The quantization of general relativity has been one of the most challenging problems in theoretical physics. Canonical quantum gravity leads to the Wheeler-DeWitt equation, which contains the problem of time. While the goal was to find some Schrödinger-like wave functional to provide quantum gravitational evolution, the Wheeler-DeWitt equation cannot provide non-perturbative evolution of quantum gravity, since the Hamiltonian, which is thought to be the time translation operator, ends up annihilating quantum states rather than evolving them over time. The quantization of teleparallel theories equivalent to general relativity has not been explored in as much detail. In this talk, I'll present a new path towards quantizing teleparallel equivalents to general relativity. This is based on the paper I recently released with a collaborator, Vipul Pandey. While this talk is highly technical and will go through mathematical details not familiar to many physicists, I will try my best to introduce as much material as possible while also showing how exotic formulations of quantum field theory generalize simpler concepts from undergraduate physics such as classical mechanics and quantum mechanics. To get to the final results, various topics needed to be introduced. We'll discuss metric affine gravity, which is the most general form of non-Riemannian geometry. Also, de Donder-Weil mechanics is a Hamiltonian formulation of classical field theory that should be taught in graduate schools but is often overlooked. Then, we'll discuss a field strength Hamiltonian formulation we introduced for this paper, which treats the field strengths as velocity fields and generalizes de Donder-Weil mechanics. This formulation will then be applied to two teleparallel equivalents to general relativity, metric teleparallelism and symmetric teleparallelism, which are two formulations that are equivalent to general relativity. Then, we'll dive into how we can recover symplectic and presymplectic geometry from multisymplectic geometry by using covariant phase space methods. Then, we'll talk about hypersurface deformations as a representation of diffeomorphisms and the Tominaga-Schwinger equation. Then, finally, we'll apply these field strength formulation to the teleparallel equivalents at the quantum level to obtain a Tominaga-Schwinger-like equation, which is conjectured to provide non-perturbative quantum gravitational evolution. And finally, we'll talk about regularization or normalization, followed by a discussion on a kind of generalization of the Wheeler-DeWitt equation. As a disclaimer, at this time of recording, our paper is available as a preprint on arXiv, but is currently being peer-reviewed with a journal. So the results presented here are somewhat preliminary. Additionally, I must stress that we did not rigorously prove that quantum gravity is solved. For instance, this paper does not resolve the issues of UV divergences in quantum gravity. Also, we technically did not prove that non-perturbative quantum gravitational evolution can be obtained. However, as we will show, there are some fundamental differences to this formulation in comparison with general relativity, which at least appears to avoid or bypass some of the aspects of the problem of time, mainly the frozen formalism. Further work will be needed to rigorously demonstrate whether the field strength formulation of teleparallel equivalents to general relativity has well-defined quantum evolution without anomalies. To summarize our findings, first consider canonical general relativity. The Wheeler-DeWitt equation applies the gravitational Hamiltonian to a wave functional that generalizes the Schrödinger wave function in quantum mechanics. Rather than evolving the system over time, it leads to h times psi equals 0 rather than a time derivative. With our approach, we consider time evolution without picking any frame by considering paths of arbitrary hypersurfaces as submanifolds of spacetime. Time evolution is implemented by considering a parameter s that characterizes which hypersurface we are considering. Considering the hypersurface deformation generator as being analogous to a gauge field, write down a covariant deformation derivative nabla sigma dot s. Physicists are stumped on the problem of time, as some authors argue that there should be a notion of timelessness, since arbitrary spacetime manifolds do not prefer a single reference frame with a single time coordinate. Our evolution equation has a sense of timelessness. Nevertheless, the covariant deformation derivative of the hypersurface wave functional equals 0. At first glance, it may seem like no evolution is obtained, but when expanding, the Tominaga-Schwinger equation is found by subtracting the term with the hypersurface deformation generator to the other side of the equation. The Tominaga-Schwinger equation in general relativity leads to the deformation generator that annihilates quantum states. However, for the field strength formulation of the teleparallel equivalence of general relativity, the deformation generator can be found, which does not seem to vanish as the Hamiltonian is no longer constrained to vanish like it is in general relativity. Well, I must say, if none of that made any sense, don't worry about it. That's what the rest of this talk is for. If you learn anything or would like to support the channel, please like this video and subscribe to the channel. Okay, now on to the good stuff, starting with metric affine gravity. While everyone has heard how general relativity curves space-time, metric affine gravity opens the door to more exotic forms of differential geometry. General relativity was introduced in a metric formulation, while gauge gravity theories are often grounded in affine formulations of general relativity. Metric affine gravity has an independent metric tensor and an affine connection. Metric affine gravity allows for more exotic forms of non-Riemannian geometry, including torsion and non-metricity, in addition to curvature. Torsion is the antisymmetric part of the connection. Recall that in general relativity, the metric tensor measures infinitesimal lengths in spacetime. The connection describes how to parallel transport vector fields over the manifold. The Levi-Civita connection is found from derivatives of the metric, which is used in the geodesic equation and describes how gravity is a fictitious force. The pseudo-Riemannian curvature tensor is found by applying a sequence of derivatives to the Levi-Civita connection, as if it was a field strength of a non-abelian gauge potential, except fully tensor valued on the global manifold without local or gauge theoretic structure beyond the diffeomorphism symmetry of the global spacetime manifold. In metric affine gravity, the affine connection decomposes into three pieces: the Levi-Civita connection from pseudo-Riemannian geometry, the contorsion tensor from torsion, and the disformation tensor from non-metricity. A clever trick to derive the Levi-Civita connection, contorsion, and disformation involves the introduction of the Schouten brace. First, recall the structure of the Levi-Civita connection. It is this combination of indices that lead to the Levi-Civita connection, which technically depends on your conventions for how the covariant derivative acts on a tensor. In our conventions, the Schouten brace is defined like this. To derive the definition of the affine connection, we take the Schouten brace of the non-metricity tensor. The Schouten brace in our conventions is defined as following, which I'm not sure if anyone has ever written down in this way. The Schouten brace of non-metricity gives the following. Expanding the covariant derivative in terms of the partial derivative isolates the affine connection plus additional terms. And a rearranging allows for the Schouten brace of torsion to be found, which forces us to include an extra term that isolates the affine connection. We can then solve for the definition of the affine connection in terms of the Levi-Civita connection, terms involving torsion in the contorsion tensor, and terms involving non-metricity in the disformation tensor. This identifies how torsion and non-metricity fit into the affine connection, which generalizes pseudo-Riemannian geometry with the Levi-Civita connection. To get a geometric intuition for what curvature, torsion, and non-metricity is, we'll introduce the concept of holonomy. Holonomy is the study of how things change when traveling along a path, typically a closed path or a loop. Curvature is given by rotational holonomy, while torsion leads to translational holonomy. Both curvature and torsion are two forms, which means that they are associated with directed area elements which correspond to the area of the loop used for studying holonomy. While non-metricity gives scaling and shearing via holonomy, it is actually a one form, not a two form, and really measures how the dot product of two arbitrary vector fields change as one parallel transports along an open path. If we travel with a vector around a loop and the vector rotates, the amount of rotation encodes how much curvature is located along that area. For instance, you could prove that the surface of the Earth is curved by walking from the North Pole to the equator, along the equator for 90 degrees around the Earth, and then walk north all the way back to the North Pole. That's only 270 degrees, 3 turns of 90 degrees, but we went in a closed loop, a curve that is topologically equivalent to a circle. So that's why we say this is non-Euclidean geometry. Circles should have 360 degrees in Euclidean geometry, not 270. Riemannian geometry or pseudo-Riemannian geometry for spacetime allows for curvature. Simply put, to find the curvature at a single point, consider an infinitesimal square in the neighborhood of that point. If we start at one corner and travel in the dx direction, then we go in the dy direction, and then we go minus dx and finally minus dy, we should end up back where we started. If we transport a vector around that loop and we find the vector rotates, then this characterizes how much curvature is found at that point and in which direction. This intuitively describes why the Riemann tensor is a 4 tensor, as there's one index for the initial vector, one index for the final vector, and 2 indices for the loop. Additionally, rotating the initial to the final vector is given by a Lorentz group transformation, a rotation of spacetime, which has 2 indices. So there's 2 indices for the loop and 2 indices for the rotation, 4 in total. If we transport anything, whether it be a scalar, a vector, or a tensor field, if that object gets translated when traveling around a loop, then that means there's torsion within the loop. Torsion is a 3 tensor because translation is characterized by a single vector, while the loop contributes 2 vectors. Although torsion relates to gauging the translations, which once again is described by a vector, unlike rotations for curvature. Also, gauging torsion relates to gauging the translations, which once again is described by a vector, unlike rotations for curvature. So the torsion tensor has 1 less index than the curvature tensor. To describe non-metricity, imagine you had 2 different vector fields and you walked along an open line. Measuring the difference in the dot product of 2 arbitrary vectors along an open line interval is the technical definition of the non-metricity tensor with respect to transport. This defines non-metricity on edges rather than areas. However, we still can find that non-metricity affects holonomy. For instance, if a vector changes its scale or magnitude after going around a loop, then this is a notion of non-metricity. Non-metricity is a 3 tensor, but for completely different reasons than torsion. Since we bring 2 vector fields across a 1D path, we get 1 global index associated with the path and 2 indices associated with the scale or shear transformations. Non-metricity therefore allows for shearing of spacetime, while torsion can be thought of as twisting spacetime, and curvature refers to a curved hypersurface or manifold. The world crystal defects perspective also helps depict non-Riemannian geometry even more clearly. Curvature is like adding or removing a wedge from spacetime and gluing it back together, which is called a disclination. Torsion is like adding or removing line defects from spacetime, which is then called a dislocation. Non-metricity is associated with adding or removing a single point, which are called interstitial or vacancy defects. So we see that in a sense, torsion is like infinitesimal curvature, while non-metricity is like infinitesimal torsion. That's because one can interpret the same defect as a single curvature defect or an infinite number of torsional defects. For instance, a wedge can be characterized by an infinite number of line defects taken at an angle. Additionally, 2 wedge disclinations can be defined to get a single line dislocation. Similarly, a torsion defect can be decomposed into an infinite number of non-metricity defects, just as a line contains an infinite number of points. Also, 2 line defects can be combined to give a 0-dimensional defect. This picture has motivated me for quite some time to wonder if non-metricity is the necessary differential geometry for quantum gravity, as it is the theory relevant for high-energy physics, which probes the smallest distances. This picture has motivated me for quite some time to wonder if non-metricity is the necessary differential geometry for quantum gravity, as it is the theory relevant for high-energy physics, which probes the smallest distances. If the Planck length implies that rulers are in some sense broken at the Planck scale, then maybe non-metricity is needed for physics near the Planck scale. This quickly made intuitive sense to me. I originally thought I was the first to derive how non-metricity was a 0-dimensional defect after reading Hagen-Kleinert's work and generalizing it to metric affine gravity. As I read more of Friedrich Hell's work, I came to realize that non-metricity was introduced by Kroner as a 0-dimensional defect when introducing the notion of relativistic elasticity theory, which was not initially intended as a theory of gravity. Rather than writing a full paper on non-metricial defects of gravity, I studied the topic during a Wolfram School project and wrote a brief summary since Kroner had found this obscure result before I was born. The observation of non-metricity as the smallest form of classical gravitation is what motivated me to study the quantization of teleparallel equivalents to general relativity, as they describe effects of general relativity, yet use differential geometry that provides a more granular or microscopic description of spacetime. Perhaps the physics of singularities, black holes, high-energy neutron star scattering, and quantum gravitational dynamics of elementary particles at high energy could benefit from non-Riemannian descriptions of general relativity. So what is non-Riemannian geometry, and how does it relate to metric affine gravity versus general relativity? In general relativity, the Levi-Civita connection is uniquely determined by the metric. In metric affine gravity, the metric tensor and affine connection are treated independently. The Levi-Civita connection is the unique affine connection with vanishing torsion and non-metricity, but contortion and disformation are added if there's torsion or non-metricity, respectively. The contortion and disformation tensor combine to give the distortion tensor. So, the non-Riemannian curvature tensor is still defined in terms of the affine connection, but now it contains additional contributions due to the presence of this distortion tensor. Within metric affine gravity is the trinity of gravity, which states that general relativity can model gravity with curvature, or one can obtain equivalent dynamics with teleparallelism and torsion, or non-metricity. Let's break this down. Teleparallel theories have vanishing curvature. The curvature is in terms of the affine connection. From 1925 to 1931, Einstein considered teleparallel theories in an attempt of unifying gravity and electromagnetism. By 1929, Landkos wrote a letter to Einstein saying he merely had a theory of gravity, which by 1976 was rediscovered and found to be equivalent to general relativity. Sometimes called new general relativity, this teleparallel equivalent to general relativity is often called TEGR or TEGR. The theory is also called metric teleparallel equivalent to general relativity because it is metric compatible, which means that it has vanishing non-metricity. This distinction is given because there's another teleparallel equivalent, which is symmetric teleparallelism, which was introduced in 1998. That theory means the antisymmetric component of the affine connection, the torsion tensor, vanishes. Symmetric teleparallel equivalent to general relativity, or STEGR, which I'll call Steger, is classically equivalent to general relativity and only has non-metricity, no curvature, no torsion. So, the teleparallel equivalents are named after what they do not have, as metric teleparallelism, or MTEGR, has vanishing non-metricity and curvature. Symmetric teleparallelism, or Steger, has vanishing curvature and torsion. By solving for the Riemannian component, it includes an additional boundary term. The bulk term leads to classical equations of motion via the Euler-Lagrange equations. In global MTEGR, one must apply constraints due to the vanishing curvature. In global MTEGR, one must apply constraints to the vanishing nature of the curvature, but this is not needed in Steger. Another complication with MTEGR is that the torsion tensor as a field strength is built from the connection directly, not a differential operator acting on the connection or metric. This leads to a bit of tension in the study of torsion, but the tension is resolved once studying local metric affine gravity, also known as gauge gravity. For gauge gravitational theories, two different spacetime indices are required. Greek letters are used for indices associated with the global manifold, while Latin letters are used for local indices. While it is possible to consider the local spacetime manifold as flat Minkowski spacetime in Riemann-Cartan spacetimes with curvature and torsion, metric affine gauge gravity with non-zero local non-metricity requires a local spacetime manifold that is independent of the global spacetime manifold. This is why metric affine gravity is thought to help with understanding the microstructure of quantum fields, although more research is needed in that direction. In metric affine gauge gravity, we now have 3 potentials and 3 field strengths. The local metric is a global scalar, yet it has 2 local indices just like metrics should. The local metric is the gauge potential for local non-metricity as a field strength. The frame field, tetrad, or Vierbein are all names for the same object, which has 1 global index and 1 local index. The frame field is the gauge potential for the local torsion tensor as a field strength. And finally, the local connection or spin connection is the gauge field for the local curvature tensor, which looks more like a typical Yang-Mills gauge boson, such as SUN, where generators are given by complex matrices that generalize the real rotation matrices found in the Lorentz group, and two local indices. When assuming the tetrad postulate, one can easily relate the global differential geometry to the local differential geometry. Essentially, the frame field can be used to convert global and local indices, similar to how the metric tensor raises and lowers global indices. So that's it. With metric affine gravity, we not just have curvature, torsion is mesoscopic, and non-metricity is microscopic. Think of curvature as cutting out a wedge and gluing space-time together. Torsion is like cutting a line with some scissors and Torsion is like cutting with some scissors in a line with infinitesimal width and gluing it back together. And finally, non-metricity adds or removes a single point from spacetime. Non-metricity is the most granular form of classical gravitation. Okay, so what if I told you that almost everybody understands Hamiltonian dynamics for relativistic field theory improperly? Not even Ed Witten, it seems, has fully noticed this. Urs Schreiber, on the other hand, gets it. What we're about to explore is the true way to generalize Newtonian classical mechanics to classical field theory, which is special relativistic. As you may recall, the Lagrangian of a point mass in Newtonian mechanics contains kinetic minus potential energy, whose action can be varied to obtain the classical equations of motion. The Hamiltonian represents the total energy operator, which is kinetic plus potential energy. This makes the Hamiltonian more intuitive than the Lagrangian, since total energy is conserved. One may apply a Legendre transformation to attain the Hamiltonian from the Lagrangian by swapping out the position and velocity space for a position and momentum space. In classical mechanics, we have 3 dimensions of space as well as absolute time. So velocity isn't really an extra dimension, it's just how the positions of objects move over time, where all observers have identical and synchronized clocks. The Hamiltonian is written in terms of phase space variables, where phase space includes position and momentum as separate coordinates. This phase space is described by symplectic geometry, which would be a 6D phase space in classical mechanics for a single particle. If one studies multi-particle systems, then the configuration space of the system leads to a 6 times n-dimensional phase space for n particles. To recap, the Lagrangian is in terms of the position and velocity, while the Hamiltonian is in terms of the position and the momentum. Hamilton's equations state that the external forces cause a change in the momentum over time, which derives Newton's law of motion in a direct and intuitive manner. A slick trick to derive Hamilton's equations is to consider the so-called canonical action, which expresses the Lagrangian in terms of position and momentum, and then applies variational calculus. Let's first derive the Euler-Lagrange equations by variational methods, and then apply those same variational methods to the canonical action to obtain Hamilton's equations. So when Paul Dirac was introducing electrodynamics, a relativistic framework, into quantum mechanics, a non-relativistic framework, in 1927, he immediately pioneered aspects of quantum electrodynamics as a relativistic quantum field theory. In his approach to quantum field theory, Dirac's canonical momentum is grounded in the non-relativistic setting because the Lorentz symmetry is not manifestly expressed. A time coordinate from a preferred inertial reference frame must be chosen to find the Dirac or canonical Hamiltonian for quantum field theory. And since it's called canonical, it must be the preferred or only way to do it. The frustration is that field theory does not quite have a symplectic generalization that is also manifestly covariant, at least at first glance. However, canonical field theory is different than Newtonian mechanics in 2 ways. First, it is special relativistic, where space and time are now relative as a single representation of the Lorentz group. Second, although it is studied in particle physics, there are no longer particles of zero volume, but fields of infinite extent and arbitrary density throughout the volume of space and over time. It is these 2 different generalizations of unifying space and time and updating particles to fields that can easily get overlooked or conflated. What we should anticipate is 2 updates to classical mechanics. First, we should expect some covariant generalization that involves the partial derivative rather than the time derivative, which works because we have relativistic fields that are varying over space-time. Second, we should anticipate that field theory should involve extra derivatives over space, as we now have evolution of fields spread out over space, not just infinitesimal point particles. These two changes support each other, making classical field theory stable and rock solid. Just look at the Euler-Lagrange equations for classical fields versus classical or Newtonian mechanics. I think it is clear that the Dirac or canonical Hamiltonian is not the natural generalization, while de D'Ander-Weil mechanics is. While my perspective may be a bit radical, I believe it's also rather conservative. If we start with the action in terms of the Lagrangian density, the cursive-looking or calligraphic L, the variational methods allow for a straightforward derivation of the field equations for arbitrary field theories from the principle of extremal action. Now that we have the field equations, let's compare this side to side with Newtonian mechanics. In Newtonian mechanics, we have velocity as a time derivative of position and momentum as the variation of the Lagrangian with respect to the velocity. Then, the equations of motion apply a time derivative to that momentum to obtain the forces that determine the dynamics of the system. These are the equations of motion. We see that first, the time derivative gets updated to a partial derivative in the Euler-Lagrange equations. And second, we see that the velocity field has a higher tensor rank than the position field, which means it has an additional spacetime index. In 1927, Dirac studied quantum mechanics and then went into relativistic electrodynamics. And then he updated his mechanics to special relativity, but then also studied the photon field as relativistic quantum field theory. In 1928, he also discovered the Dirac spinor, which describes the electron, and he discovered the mathematical structure leading to the discovery of the positron, electron's antimatter particle with the same mass and total spin, but opposite electric charge. One can reasonably argue that the Dirac equation is one of the top 5 most important equations in theoretical physics. And as he was juggling all of these amazing achievements, perhaps he did not realize that the natural generalization of the Hamiltonian is to consider de D'Ander-Weil mechanics. As such, the so-called canonical Hamiltonian for field theory is based on the methods of Dirac that originally were used in introducing quantum electrodynamics. The canonical Hamiltonian focuses on energy in a specific frame, which requires a preferred time coordinate and forces one to pick a Lorentzian reference frame, rather than keeping the Lorentz covariance manifestly expressed in terms of 4-vector quantities. The time derivative in a specific frame, rather than the partial derivative, is utilized to define the velocity and momentum fields, which is what allows for symplectic geometry. This is why people thought it was the natural generalization of classical Hamiltonian methods, because you naturally got the symplectic geometry with Dirac's methods. However, when looking at the Euler-Lagrange equations for fields, both de D'Ander and Weil realized in the 1930s that it is more straightforward to do something else. The Euler-Lagrange equations involve partial derivatives, not just time derivatives. So if a scalar field phi generalizes the position of a particle, then the partial derivative of that scalar field is the natural generalization of the velocity, not just the time derivative of that field. We call this the Pauli velocity field. From there, a Pauli momentum field can be defined by varying the Lagrangian with respect to the velocity field. We call it a Pauli momentum field because the phase space geometry is referred to as Pauli symplectic geometry. And one can study any relativistic field theory, write down the action, and derive the generalized Hamilton's equations or de D'Ander-Weil equations. Boy, I'm already way behind schedule and gotta get to the good stuff. All this to say that classical field theory has a configuration space that generalizes Hilbert spaces with a fiber space of fields and base space of spacetime, such that classical fields are sections of the fiber bundle. What all that means is simply that fields are evaluated at a point in spacetime. That's all it essentially means. But doesn't it sound super fancy and complicated when I say words like fiber bundle and base space? Okay, but I don't want to wimp out and say we're out of time. Here's the deep and nitty-gritty of the technical details, the down and dirty on what polysymplectic and multisymplectic geometry actually is. The problem is there's at least 5 different constructions in total, all of which are mathematically sound. These differing mathematical definitions have left physicists confused for decades, so I'll try to make it as simple as possible. Polysymplectic geometry refers to the higher tensor rank of the momentum field, a polysymplectic field. For instance, if the field phi A is a position field, then the corresponding Pauli velocity field is the partial derivative of that field, partial mu phi A. then the Pauli momentum field is the variation of the Lagrangian density with respect to that Pauli velocity field. Now, multisymplectic geometry starts with the notion of a jet bundle and essentially defines classical fields formally through the notion of the fiber bundle construction I just mentioned. Spacetime is the base manifold, and the fields are coordinates of the fiber space. The fields evaluated at a point are a section of the bundle. From there, I found at least 4 different formulations of multisymplectic geometry. There is the reduced, extended, generalized, and restricted multisymplectic bundles. And the names are confusing to remember. Which is the reduced and which is the restricted? What about generalized versus extended? So to start, a jet bundle describes the geometry of classical field theory. We have spacetime as a base manifold, but then we have fields as fibers, yet the fields evaluated over spacetime are taken as sections over the base space, meaning that fields are functions of spacetime, where spacetime is given by some manifold. The first jet bundle also provides the Pauli velocity fields as coordinates within the fiber space as well, which links polysymplectic geometry to multisymplectic geometry. The reduced multisymplectic geometry has enough information to define the fields and Pauli momentum. But the DDW Hamiltonian, where DDW stands for de Waal, is not encoded in the geometry. The extended multisymplectic geometry is the most common and adds an energy density scalar as an additional coordinate in a fiber space, which essentially encodes the DDW Hamiltonian density. The generalized multisymplectic geometry contains an extra tensor that includes the Legendre transformation factor of the Pauli velocity times the Pauli momentum, except 2 indices are also not contracted. Finally, the restricted multi-momentum bundle has the same coordinates as the reduced multi-momentum bundle, but is introduced using vertical cotangent bundles. Essentially, the reduced and restricted multisymplectic geometry allows for everything to be defined, but it doesn't give a canonical multisymplectic form in terms of a potential, which was not satisfactory to some mathematicians. The extended multisymplectic geometry includes an energy density such that the Hamiltonian is encoded in the geometry itself after choosing a Hamiltonian section. Finally, the generalized multisymplectic geometry includes an additional tensor whose trace contains information needed to find the Hamiltonian, or it may have a loose connection to the stress energy momentum tensor. So different authors have worked with different mathematical definitions of multisymplectic geometry or used the polysymplectic geometry, which has made it difficult for physicists to digest. Okay, so the main lesson here is that the Euler-Lagrange equations for relativistic field theory naturally suggest multisymplectic or polysymplectic geometry, not symplectic geometry. This is because relativistic classical fields have spacetime evolution of fields as a density of volume, not a point in space with absolute time. These 2 different generalizations seem to provide a nice harmony for the structure of classical field theory. However, this does obscure the notion of quantization, at least according to Dirac's methods of mapping Poisson brackets to commutators. Grunwald demonstrated that Dirac's approach to quantization is not rigorous and only works for Lagrangians that do not go beyond quadratic order in the position or velocity variables or fields. Since I'm interested in exploring theories beyond general relativity eventually to see whether they have better behavior with respect to so-called ultraviolet divergences in quantum gravity, I cannot always rely on Dirac's quantization methods, despite them always working for everything we're taught in the textbooks. But we'll get to quantization later, as there's another trick I'll mention that most of the multisymplectic community seems to be overlooking. Still, the natural Hamiltonian for classical field theory is the de Waal Hamiltonian, which obtains the DDW equations as polysymplectic generalization of Hamilton's equation. So let's now think about the Hamiltonian classical field theory for the trinity of gravity. What is the best framework to encapsulate them all? Well, first, let's review canonical general relativity to see why quantum gravity appears to be so problematic from various angles. Covariant general relativity has primary Hamiltonian constraints from Legendre transformation degeneracy. The singular nature of the Legendre transformation leads to a vanishing Hamiltonian, as well as a 3 momentum to be vanishing due to these constraints. To end all of these Legendre degenerate constraints once and for all, I decided to study the field strengths themselves, not just the derivatives of the fields, as generalized velocity fields. Because in field theory, the velocity fields are already generalized velocities in a non-intuitive sense, due to them being polysymplectic and allowing for variations over time and space. Since the gauge theories have 1-form potentials and 2-form field strengths, The two form is an anti-symmetrization of the de Donderweil Pauli velocity. Our field strength formulation removes a constraint, as the symmetrization of the momentum fields must be constrained to vanish for gauge theories in de Donderweil mechanics. Since the field strengths themselves already contain all of the physical information, it makes more sense to work with these as a velocity field, as it removes the necessity for a constraint. Now, with the field strength Hamiltonian approach to Maxwell's equations, everything becomes much simpler. We take the Lagrangian, we define the generalized velocity field as the field strength, and then we find the momentum field strength by varying the Lagrangian with respect to the field strength. We use that to find the Hamiltonian. We then apply the first field strength Hamilton's equations to obtain the field strength back in terms of the momentum field strength. Then we applied the second field strength Hamilton's equations to obtain what sources electromagnetic fields. And voila, let there be light. It is as simple as could be. By treating the field strengths themselves as the dynamical velocity fields, this immediately focuses us on the physics rather than additional unphysical degrees of freedom. It also keeps the manifest Lorentz covariance so that the equations can be more easily manipulated without separating space and time or electric and magnetic fields. Anyone who has ever derived Maxwell's equations from Dirac's Hamiltonian's methods might be a bit surprised to see how easy it is to obtain the equations of motion with this Hamiltonian formulation. Additionally, de Donderweil mechanics would require the symmetric part of the Pauli momentum to be constrained to vanish. From our standpoint within the field strength formulation, the momentum field strength is defined to be antisymmetric whenever dealing with field strengths that are two forms. So no constraint needs to be applied. From this vantage point, it is as if physicists always throw in additional fictitious momentum field components for no reason, and then have to carry around all this extra baggage to remind themselves that some of the components in the tensor are zero. Now, this formulation is also quite natural to work with metric affine gauge gravity. Here we gauge the affine linear group, which decomposes into the Lorentz group, the translations as found in the Poincare group, and the shear and scale transformations encoded in the quotient space GL4R modded out by the Lorentz group. What this provides is that the local metric GAB is the gauge field for local non-metricity as a field strength, Q rho AB. Gauging the translations gives the frame field, E mu A, as a gauge potential with the torsion tensor, T rho mu nu, as the field strength. Finally, the Lorentz rotations of spacetime provide the local connection or spin connection, omega mu AB, as the gauge potential, with the curvature tensor, R rho sigma AB, as the field strength. The field strength Hamiltonian formulation allows us to treat the curvature, torsion, and non-metricity tensors as generalized velocity fields, which has precedence within the metric affine gauge gravity community, such as the work of Hell and Obukhov in the 1980s. This new contribution here is to carry through with the Legendre transformation to find a Hamiltonian density for metric affine formulations. The Hamiltonian of the teleparallel equivalence to general relativity had never been studied in this manner. This is particularly interesting because while the Einstein-Hilbert action is linear in the curvature, both the metric and symmetric teleparallel equivalents to general relativity are quadratic in torsion and non-metricity respectively. The Legendre transformation itself does not introduce any Hamiltonian constraints. This is particularly relevant as the Wheeler-DeWitt equation leads to a vanishing Hamiltonian operator that annihilates states rather than time evolution. Therefore, in pursuit of exploring whether the teleparallel equivalents to general relativity have improved quantum behavior or not, the field strength formulation was introduced specifically to provide a formalism to study these gravitational theories in a Hamiltonian formulation without a preferred time coordinate and without any Hamiltonian constraints from Legendre degeneracy. Since physicists looking into general relativity were struggling to disentangle gauge-redundant degrees of freedom from actual quantum gravity dynamics, I figured it might help to not introduce additional unphysical momentum fields that are constrained to vanish if we are looking to focus on the dynamics. Dirac's treatment of how to deal with the constraints is elegant and mathematically beautiful, but it is a lot of work and unnecessary in the field strength Hamiltonian formulation for quadratic gauge theories. In summary, the field strength Hamiltonian formulation treats the field strength as a generalized velocity field. It applies to any field theory that is quadratic in a field strength, defined as any first-order differential operator acting on the field. or even if it's not a derivative, we actually worked it out for global torsion as well. So it can be a derivative or not. And this allows for a modified Euler-Lagrange equation to be derived from variational methods, which accounts for the change of variables from the de Donderweil Pauli velocity to the field strength as the velocity variables. This allows for a covariant momentum field strength to be found that allows for a nice Legendre transformation, ensuring that at least some kinds of unphysical degrees of freedom are not included into the Hamiltonian analysis. Finally, the Hamiltonian leads to a field strength formulation of Hamilton's equations as shown here. Additionally, the teleparallel equivalents admit a gauge-theoretic interpretation. Gauge theories have provided some of the most successful quantum field theories, such as quantum electrodynamics and Yang-Mills theory. So the hope is that studying gravity as a local gauge theory will also help alleviate some of the issues with quantizing general relativity. Metric teleparallel equivalent to general relativity, abbreviated MTGR, is a theory that is quadratic in torsion. It is found by considering the total Ricci scalar from non-Riemannian geometry, specifically a teleparallel Cartan geometry with torsion. The non-Riemannian Ricci tensor can be found by first decomposing the affine connection into the Levi-Civita connection and the contorsion tensor, which is torsion's contribution to the affine connection. The Lagrangian for MTGR is found by subtracting away the Riemannian curvature from the total curvature, which remarkably allows for the Einstein-Hilbert action in terms of the Levi-Civita connection to be expressed completely in terms of the torsion tensor. It also naturally makes the action quadratic, which is more similar to other gauge theories like Yang-Mills theory. And MTGR is best studied formally as a local gauge theory, as this leads to the frame field as the natural gauge potential associated with the translations of spacetime. Feynman has most famously mentioned that gauging translations in Minkowski spacetime was essential for perturbative quantum gravity, but he was more grounded in the notion of global diffeomorphisms on the global manifold and less so with torsion. Even the path integral of hydrogen could not be solved by Feynman. He left it out of his textbooks for that simple reason, as it was not deserving. He left it out of his textbooks for that simple reason, as it was not deserving to be mainstream yet. However, he gave the problem to Hagen Kleiner, who wrote in his 1,000-page textbook on path integrals that he found how the path integral of hydrogen can be solved by recognizing that the singular hydrogen potential requires a defect associated with torsion in order to resolve the issue. So, Feynman wanted to be grounded in torsion, but was following Dirac's definition of gauge symmetry and missed how torsion is required to describe the path integral of hydrogen and is also the gauge field for the translations. And once again, the translations are the gauge group of metric teleparallelism, which is fascinating. It also leads to a well-defined gravitational stress-energy-momentum tensor, while general relativity can only resort to quasi-local energy definitions. There are gravitational stress pseudotensors in general relativity, but they are not truly valid tensors, which makes their properties a bit less clear and difficult to firmly establish. So, by taking the global Ricci curvature and solving for torsion, we can relate this to local torsion, which is trivial with the tetrad postulate. This allows us to have a dynamical field theory in terms of the frame field that is gauged by translations, a four-dimensional abelian Lie group that is typically used to extend from the Lorentz group to the Poincare group. Now, we introduced the frame field formulation specifically to deal with metric teleparallelism. The Pauli velocity of the theory is given by the partial derivative of the frame field. The Pauli momentum field would be in terms of the variation of the action with respect to the Pauli velocity. However, that would require us to constrain the symmetric part of the Pauli momentum field to vanish. My obsession has been to remove these constraints as one typically constrains a Lagrangian for systems like a ball tied to a rope. I don't see how field theory is like balls tied to ropes, so I've always intuitively not loved how field theory often uses Hamiltonian constraints, which was a technique largely popularized by Dirac. Once again, I love Dirac for all of his contributions, but I think in this one instance, the field may have been swayed too heavily by his preferences. So, if we simply define the generalized velocity field as the torsion tensor itself, then we can derive a momentum field strength without any Hamiltonian constraints. There is a precedent for this in the metric affine community from Obakov and collaborators, but they never seem to explore a Hamiltonian density from these generalized momenta. This is partially due to the obscurity of both metric affine gravity and Dodon or Weyl mechanics. For general relativity, it requires constraints regardless of the choice of velocity fields, as the Einstein-Hilbert action is linear in curvature. However, metric teleparallel equivalent to general relativity is quadratic in the torsion tensor. This inspired the field strength formulation so that no constraints on the Hamiltonian or momentum fields are required to perform a Legendre transformation when the field strength formulation is utilized. And the long story short is you can use this formulation to derive the equations of motion of metric teleparallelism. To sketch how this works, we take the action, we find the momentum field strength in terms of the torsion tensor, and then we invert it. To do so, it was convenient to find all the traces of this momentum field strength. This allows for the torsion traces to be found in terms of the momentum field strength traces, which helps to then solve for the torsion tensor in terms of that momentum field strength. This allows for the field strength Hamiltonian density to be found in terms of the frame field as the dynamical field and the corresponding momentum field strength within a generalized multisymplectic geometry. After the field strength Hamiltonian is found, one can apply the first Hamilton's equations to confirm the definition of the torsion tensor. Then from there, this definition can be plugged into the second Hamilton's equations to find the equations of motion. It is worth highlighting that with the field strength formulation, all of the gravitational fields are found as the kinetic piece. This is because the Hamiltonian density is equal to the Lagrangian density. So rather than defining kinetic versus potential as propagating versus interacting with anything, including interactions with itself, the potential truly refers to the sources of gravity, which simplifies the Hamiltonian analysis. Now, let's look at symmetric teleparallel equivalent to general relativity. Okay, students, so what is the name of the teleparallel equivalent theory that contains non-metricity, and why is it named that? Ooh, metric teleparallelism because it has the metric as the gauge field? No, that is completely wrong and backwards. Metric teleparallelism is metric compatible. Well, what does metric compatible mean? It means that the non-metricity vanishes. Well, what does non-metricity mean? It is the covariant derivative of the metric tensor. Okay, but what does that mean intuitively? It describes how the dot product of two arbitrary vector fields would change along an open line interval. In gauge theory, it is the only gravitational field strength that is a one form, rather than a two form like curvature and torsion. As such, it is technically defined along a line, not with a loop. You know, the metric affine gauge gravity that does not use the tangent space because it has to introduce an entire tangent manifold to obtain the local non-metric structure of space-time, just in case there's a small chance that there's... Okay, I'm not sure if any of this is helping. Okay. Imagine you are Eric Weinstein surfing across proto-space-time with your favorite ruler and protractor in your pocket. It's a ruler and protractor gadget that can measure infinitesimal space-time intervals and angles. According to his theory, we can boost beyond the speed of light by applying scale transformations within the double cover of GL4R. This is the mathematical framework necessary for his warp drive proposal. Okay, cool. Eric Weinstein, hello. Are you listening? I must tell you, if you are seriously interested in pursuing your proposal for warp drives from non-Riemannian geometry via scale transformations, you might be interested in how the metric transformations within GL4R, yet outside the Lorentz group, are given by non-metricity, not torsion. GL4R, or its double cover as the isometry group of your quotient space giving proto-spacetime in geometric unity, literally corresponds to the gauge degrees of freedom of non-metricity, which has the metric as the gauge gravitational potential. This is why you should look further into the research of metric affine gravity that was kicked off in the 1970s, which embraces non-metricity. There is not more time. We need to get off this rock before I'm afraid the worst is going to come to humanity. Wait, I thought you were teaching us about symmetric teleparallelism. Right. So why then is symmetric teleparallelism called symmetric? Oh, I get it. It's because the metric is the potential, which is symmetric. No, you've got it completely wrong. Well, you are right that the metric is the potential, but no, that is not why the theory is called symmetric teleparallelism. It is called that because... So wait, you were telling me that both metric teleparallelism and symmetric teleparallelism are defined by what they don't have, not the geometries they do have? Yes, precisely. After all, teleparallelism means that the non-Riemannian curvature vanishes. And so, we can go through the same song and dance with Steger as we just did with Integer, except this time, we can work with a global formulation classically. Essentially, the non-metricity tensor is the velocity field, and the so-called non-metricity superpotential of Steger is proportional to the momentum field strength. In this case, it is also equivalent to the covariant map of the Pauli momentum field of the metric, since non-metricity is a one form, unlike torsion as a two form with the anti-symmetrization in the two global indices. Non-metricity only has one global index for the local non-metricity tensor. However, we can also simply work with the global formulation without loss of general relativity and simplicity in terms of using the same indices, avoiding the frame field. For symmetric teleparallel spacetimes, the non-Riemannian Ricci scalar can be expanded in terms of the pseudo-Riemannian Ricci scalar in terms quadratic and non-metricity. We can do the same exact thing that we did in Integer to derive the equations of motion. We can start with the action, we can derive the generalized momentum field strength, which in this case is basically the same thing as the covariant Pauli momentum. Then from there, we can derive the Hamiltonian density, and then apply the field strength Hamilton's equations, which in this case would be the same as the de Donner-Weil equations, and then we can obtain the equations of motion for Steger. Now, the next step in our studies was inspired by something I noticed a few years prior. There were a few papers that I came across where the Pauli momentum was mentioned without the authors realizing its significance within the context of de Donner-Weil mechanics or multisymplectic geometry. This started with the work of Černkovič, which was quickly adopted in collaboration with none other than Ed Witten. They studied toy models in string theory and brought these methods down into the language of quantum field theory, which allowed for more practical adoption for the entire physics community in relation to a set of covariant and presymplectic realizations of relativistic field theory. See, if you never had a weird uncle who had mentioned the term polysymplectic or multisymplectic geometry, you would be looking for a symplectic description of relativistic quantum field theory, as symplectic geometry is the typical description of how Hamiltonian dynamics and field theory works, especially those who followed the so-called canonical approaches that were popularized by Dirac. Now, what we mean by canonical refers to this presymplectic geometry, but oftentimes it gets associated with Hamiltonian dynamics. However, Witten and collaborators just stopped at defining this symplectic or presymplectic potential, and they never actually connected it to a Hamiltonian. So, Witten and Černkovič were after a covariant and canonical description that was also symplectic. Yet, their definition of a symplectic currently actually used the definition of the Pauli momentum without them realizing it. This observation inspired me to combine the covariant phase space methods or generalized boundary methods with polysymplectic geometry. Combining these two fields allows for a Hamiltonian in terms of a polysymplectic momentum, which can be pulled back to a submanifold that contains symplectic or technically presymplectic geometry. This notion of covariant versus canonical is also at the heart of why loop quantum gravity is bifurcated into two groups. First, there were the canonical methods associated with loop quantum gravity, and then later, the covariant methods became more developed. The canonical methods are grounded in the Hamiltonian and prefer a particular time coordinate, while the covariant methods are more grounded in the Lagrangian, with manifest Lorentz covariance seen explicitly in the formalism. It is as if the entire field of loop quantum gravity cannot see how to find a single framework that is both canonical and covariant. However, I should mention that some researchers of loop quantum gravity are more than just that. These are researchers of quantum gravity in general, willing to explore various ideas, including the notion of covariant phase space methods. First of all, Witten and Černkovič utilized the de Donner-Weil Pauli momentum within their definition of the symplectic momentum density. Independent of Černkovič and Witten, Robert Wald has also came across these methods under another guise of Noether symmetry, which provides the link by constraining a polysymplectic Noether current. Other authors referred to generalized boundary methods, which were essentially talking about the same structures, but none of these communities had connected the dots to realize that there had been the most standard covariant Hamiltonian density explored by two of the best theoretical physicists of the Einstein era, namely the work of Weil and de Donner from the work in the 1930s and 40s. Classical mechanics exhibits a canonical Hamiltonian with Galilean covariance and symplectic geometry. In classical and quantum field theory, it would be nice to obtain a canonical Hamiltonian that is Lorentz covariant and symplectic, or at least pre-symplectic. By canonical, we really mean that there's some canonical variables, namely a field potential or position field, and a conjugate momentum field that satisfies some canonical relationship with Poisson brackets at the classical level or a commutation relation at the quantum level. It also can refer to the canonical structure of the geometry itself. When we say the theory is manifestly Lorentz covariant, we mean that it can be written in a language that exposes the Lorentz symmetry of the representations of all the fields within the theory. In other words, we see all of the 4 vector indices explicitly. Since electrodynamics has a special relativistic photon field, it is Lorentz covariant, as in, we understand how to properly transform the field from one reference frame to another. It is the foundational backbone of what allows us to resolve Einstein's paradox about how light moves at the speed of light to both observers on a train and off a train. By symplectic, we mean that there is an associated phase space geometry with symplectic structure, such as a symplectic form and a symplectic current, etc. Finally, by pre-symplectic, we mean that the pre-symplectic geometry encodes additional gauge redundant information within the fields. In classical mechanics, a particle can physically explore all of phase space, but with quantum fields, we often include fields with additional gauge redundant degrees of freedom that are unphysical. To enlarge the symplectic geometry to include the full off-shelf fields for exploring quantum evolution, it is convenient to recover the pre-symplectic geometry, which includes this gauge redundancy. One can then average over all gauges and quotient out by that averaging, or essentially divide out by the gauge orbits to obtain the symplectic geometry. So, the symplectic geometry can typically be recovered from the pre-symplectic geometry. As far as I have studied, I found 3 different proposals for obtaining symplectic geometry from multisymplectic geometry. First, the multisymplectic geometry community has mostly explored the language of differential geometry. So they might use an infinitesimal dx mu and contract that with the Pauli momentum to obtain a covariant yet pre-symplectic momentum field. However, they don't really fully see this as symplectic geometry because they're still embedded in the multisymplectic geometry community. Second, Konachikov has used gamma matrices in his Dirac equation-inspired approach, which is more interested in obtaining a Dirac equation than a Schrödinger equation, both of which have first-order time evolution. Third, there is a notion of combining the covariant phase space methods with the multisymplectic geometry community, which is what I wanted to do. Since this third option is essentially established within the literature but never typically stated this clearly, we will demonstrate that one can combine de Donder-Weil mechanics or generalizations thereof, such as the field strength Hamiltonian formulation, and we can bring this to the covariant phase space method and apply further tricks by introducing hypersurfaces. This third idea is the one I hadn't seen many people exploring or considering, so we developed the formulation further. The presymplectic field strength can be found by adding a unit vector n mu to the Pauli momentum field or momentum field strength. This allows for us to decompose the Pauli momentum into normal and tangential components. As hypersurfaces deform continuously into each other, one can study the normal component of the Pauli momentum to see what contributions to the Pauli momentum contribute to the momentum flux. To see the Pauli momentum contribute to the momentum flux through the boundary of each hypersurface, which describes the dynamics, rather than the internal gauge reparameterizations of the same physical state. This leads to a presymplectic hypersurface potential and a presymplectic hypersurface symplectic form. A form of Poisson brackets may be found for classical phase space fields evaluated on these hypersurfaces. Feynman diagrams are the most famous depiction of computations from quantum field theory, as their topological diagrammatic structure provides some intuitive conception of how interactions of quantum fields actually work. However, in the early days, when Feynman first presented his diagrams around the 1940s, it was the work of Julian Schwinger that immediately caught the attention from everyone, as the rigor of his work was undenied. Schwinger almost prided himself on being able to compute things that nobody else could. He really did try to explain it in his work, but he truly was brilliant in a manner that not many could follow. However, the results of the fruit of his labor were undeniable, commanding him the greatest respect for his ability to compute aspects of quantum electrodynamics. In particular, the Tominaga-Schwinger equation was one realization of an evolution equation. As it turns out, the Japanese physicist Tominaga was developing essentially the same ideas relating to quantum electrodynamics. And in this case, Tominaga first introduced an equation in 1946 that eventually led to a Schrödinger-like kind of evolution, except for the relativistic quantum fields like quantum electrodynamics. This worked by studying evolution along hypersurface deformations in Minkowski spacetime. The Tominaga-Schwinger equation works as follows. Consider a hypersurface capital sigma, which is a three-dimensional submanifold of the four-dimensional spacetime manifold, with coordinates lowercase sigma. This could be like a rest frame of space within a single moment of time, or it could be some other configuration. By considering a continuous path of hypersurfaces that infinitesimally deform into each other, a covariant realization of quantum evolution is found for relativistic quantum fields. A path is formed by continuously deforming the hypersurfaces to give an infinitesimal structure. For instance, if we have sigma 1 and sigma 2 as two sequential hypersurfaces along a path S, then we can define a derivative dds in terms of a variation with respect to the deformation vector. The deformation vector depends on the position of the boundary and defines how much and in which direction the boundary gets deformed at each location. Another way to characterize the evolution of these deformations is with a deformation operator. This is somewhat analogous with how the Hamiltonian as the energy operator evolves the system over time, except now we have a hypersurface deformation generator that evolves the system across the path of deformations. The deformation operator can be found by integrating the flux of the Noether current associated with diffeomorphisms. In other words, hypersurface deformations generate diffeomorphisms. The Noether current is found by considering the polysymplectic canonical 1 form by varying the fields with respect to the diffeomorphisms, and then subtracting a term with the deformation vector multiplied by the Lagrangian density. Or we can do a Legendre transformation to express the Lagrangian in terms of the momentum field times the velocity field minus the Hamiltonian. Taking the inner product of them can be seen as a generalization of the Schrödinger equation, where the Hamiltonian is replaced with the hypersurface deformation operator, and the time derivative is replaced with the deformation derivative dds. By taking away functional fields, states for relativistic quantum field theory can be evolved. The hypersurface deformation derivative provides a natural interpretation of time evolution without preferring a single time coordinate. Now, technically, Tominaga and Schwinger introduced an equation for state evolution in a Hilbert space through hypersurfaces. However, this state can be realized as a wave functional of fields, which is how we will frame it. Next, it is natural to generalize the position and momentum operators in quantum mechanics to include position and momentum field operators. See, in classical theory, we typically have Poisson brackets, which satisfy canonical relations as follows. When generalizing to canonical approaches to field theory, the field generalizes the position, and the momentum field is defined as the variation of Lagrangian with respect to time derivative of the field. This leads to a natural generalization. In generalizing the canonical approaches to field theory, the field generalizes position, and the momentum field replaces the momentum. We can take derivatives with respect to the field and momentum and then update the definition of the Poisson bracket for a natural generalization for field theory. Dirac's prescription for quantization is to replace the classical Poisson brackets for quantum commutators with an extra factor of I times h bar on the other side of the equation. This can also be generalized to fields, leading to a Dirac delta function as a distribution that only fires when the two fields are evaluated at the same position. When generalizing to field theory with polysymplectic geometry, since the polymomentum field is higher in tensor rank than the position field, this leads to an awkward situation. The precise definition of the Poisson bracket is not immediately clear, which has led to a plethora of studies on various different types of brackets in the de Donderweil and multisymplectic geometry community. These differences make it more difficult for a mainstream formulation to get canonicalized and widely adopted, which further motivates why quantization of de Donderweil mechanics has not been explored as much. While there has been some work on quantization with polysymplectic geometry, such as Kanachikov's precanonical quantization, most of the work on de Donderweil mechanics has been with studies of classical theory. However, by combining the covariant phase space methods, this simultaneously allows us to bring in polysymplectic geometry or the generalized structures such as the field strength Hamiltonian formulation and bring it into a language with hypersurface deformations, which is natural for the Tominaga-Schwinger equation. Additionally, it provides a hint on how to generalize Poisson brackets and commutators. This motivates our next topic, which is the field strength Hamiltonian and how it leads to a Tominaga-Schwinger-like equation. To quantize fields in the field strength Hamiltonian formulation, we seek a natural definition of a symplectic or presymplectic momentum field operator. This can be done by using the unit vector normal to spacetime that is in the hypersurface. Rather than initially quantizing the entire polysymplectic momentum field, we instead quantize the normal component and identify that with the generalization of the momentum operator in quantum mechanics. Just as the momentum operator p hat equals minus I h bar ddx, the presymplectic momentum field operator is equal to minus I h bar dd phi for the field phi. Since we want to formulate a Tominaga-Schwinger equation for field strength Hamiltonian formulations, the deformation generator must also be generalized to a quantum operator. This requires us to include the entire Lagrangian or Hamiltonian in the quantum deformation operator, so we need a definition of the entire polymomentum as an operator. Consider a general field strength Lagrangian which is quadratic in the field strength and may have some potential that depends on the fields. The kinetic term is given by a family of coefficients encoded in a single tensor, which is called the polysupermetric, as it is the polysymplectic generalization of Wheeler's supermetric. Our paper coined the term polysupermetric as I hadn't seen this explicitly proposed in the multisymplectic geometry community. The Hamiltonian density turns out to be given by the inverse polysupermetric, which is used to contract with the polymomentum fields. This works for de Donder-Weil mechanics or the slightly more general field strength formulation that we proposed. The Lagrangian is quadratic in the field strengths, and the Hamiltonian is quadratic in the conjugate momentum field strengths. The polysupermetric and the inverse polysupermetric must satisfy these symmetry properties and must satisfy the following identity, which can be thought of as a generalized metric for fields. The prescription that we proposed was to separate the polymomentum operator into the normal and tangential components, where the normal component was previously defined. That is the presymplectic component that is proportional to the variational derivative with respect to the fields. The tangential component was taken to be given by the tangential component of the polysupermetric times the polyvelocity field, now as an operator. Since the momentum field strength is defined as the polysupermetric times the field strength, this is a natural place to obtain the components of the momentum field strength operator that are not associated with the presymplectic geometry. And so, this allows us for a full definition of the momentum field strength operator, which decomposes into the normal component that is presymplectic and the tangential component obtained from the Lagrangian. This allows for the quantum hypersurface deformation operator to be defined. When taking two independent deformation vectors xi and eta, the Poisson bracket of two hypersurface deformation generators with respect to xi and eta, respectively, leads to the hypersurface deformation generator of the Lie bracket of xi and eta. This generalizes to quantum theory as a relationship between the commutator of two hypersurface deformation operators equaling I h bar times another hypersurface deformation operator. Whenever the commutator algebra is satisfied as above, the theory is considered to be anomaly free. Obtaining anomaly freedom is crucial, which is not something that we proved in this paper. However, if anomaly freedom is found, then an evolution operator becomes well defined, which evolves from one hypersurface sigma 1 to another hypersurface sigma 2. Then the operator is given by a path-ordered exponential of an integral over the quantum hypersurface deformation operator. Going back to the Tominaga-Schwinger equation, it has also been explored in the context of gravity. When studying the hypersurface deformation algebra and general relativity, it only ever produces bulk gauge redundancies, never physical time evolution. This seems to be another facet of the problem of time. No matter how we look at general relativity, whether it be the Wheeler-DeWitt equation or the Tominaga-Schwinger equation, one keeps obtaining equations that look like they should lead to the dynamical evolution of quantum gravity. However, upon further inspection, one finds that the equation doesn't actually evolve the system. Instead, it annihilates the quantum states or evolves gauge-redundant information associated with hypersurface deformations rather than dynamical evolution of the theory. The hypersurface deformations in the Tominaga-Schwinger equation also got people such as Dirac and later Teitelboim thinking about hypersurfaces in the context of general relativity. Dirac had an elegant approach to studying Hamiltonian constraints in the context of field theory, which treated diffeomorphisms as a kind of gauge symmetry within general relativity. By the mid-1950s, Dirac had written about the Hamiltonian formulation of general relativity, which also led to the work of Arnouet, Desser, and Misner by 1959. This had established what is now called canonical quantum gravity, as if it is the authoritative way to obtain quantum gravity. The only problem is, it doesn't work. Even if one tries to bring the Tomonaga-Schwinger equation into general relativity, it sounds like an elegant idea, as according to Dirac's definitions, the diffeomorphisms do act as a gauge symmetry that can be treated infinitesimally to vary the metric tensors. However, after studying how those diffeomorphisms can lead to hypersurface deformations, it still turns out that those hypersurface deformations only modify bulk information that is gauge redundant transformations, rather than providing physical dynamics. As we'll discuss later when diving into the Wheeler-DeWitt equation, in canonical quantum gravity, general relativity is known to have the problem of time. The roadblocks associated with the problem of time seem to largely stem from the fact that the canonical Hamiltonian of general relativity is constrained to vanish. If the Hamiltonian vanishes, how can we get valid time evolution? One can pursue de Donner-Weil mechanics with general relativity instead of the canonical approach, but this does not change the fact that the Einstein-Hilbert action is linear in the curvature. As a result, whether we use the Hamiltonian methods popularized by Dirac or the manifestly relativistic de Donner-Weil formalism, the Legendre transformation of general relativity is always singular. This fundamental limitation of the quantization of general relativity motivated me to further study the teleparallel equivalence to general relativity. After collaborating on a paper with the mathematician Luke Hoffman and a Wolfram Institute physicist Xerxes Arsiwalla, another Indian researcher named Vipul Pandey reached out to me to discuss how to take ideas further from our previous work. We focused on looking at the trinity of gravity, which clarifies how curvature, torsion, and non-metricity are found in three classically equivalent theories of gravity, namely general relativity, metric teleparallelism, and symmetric teleparallelism. However, the quantization of the two teleparallel theories has gotten very little study in comparison to general relativity. Most notably, the teleparallel equivalents are quadratic in the torsion and non-metricity tensors. This is curious, as linearized gravity is also quadratic in a similar manner, except with the partial derivative. However, the teleparallel equivalents give the full nonlinear structure of general relativity. It also have a quadratic Lagrangian. Additionally, recall that people were trying to use the diffeomorphism invariance of general relativity to get the evolution. However, we now know that general relativity is not a gauge theory in the same way that Yang-Mills theory is. So we shouldn't expect to get dynamics from this redundant gauge information at the global level. Nevertheless, the teleparallel equivalents are true gauge theories, suggesting that the gauge symmetry, when treated locally, might actually give dynamics, just as electrodynamics and Yang-Mills theory can give dynamics. These two teleparallel equivalents to general relativity seem to initially bypass the first major obstruction associated with the problem of time and general relativity. I should be careful when I say this, as these are still very early results and is just one paper. The full structure of quantization of teleparallelism is still not understood. Additionally, I suspect there will be issues, such as ultraviolet divergences at high energies. However, a major facet of this problem of time is called the frozen formalism, which relates to this notion of a lack of evolution due to a vanishing Hamiltonian operator. By working with the teleparallel equivalents, the Legendre transformation becomes non-singular. This means that the Hamiltonian is not constrained to vanish right off the bat like it is in general relativity. Now, there's a lot of additional tests that are required to prove that we have true quantum gravitational evolution, but we are able to write down a Tomonaga-Schwinger equation for the teleparallel equivalence to general relativity. And as far as we can tell so far, it looks worthwhile to study further, as no obstructions have been found yet. Further analysis of the evolution to see whether it evolves gauge redundant information alone or whether it provides true dynamical evolution is warranted. However, the fact that the Hamiltonian does not vanish does provide some motivation to suspect it could. Additionally, the teleparallel equivalents can both be formulated as a gauge theory in a manner that general relativity cannot. The translations are the gauge group of metric teleparallelism, and the quotient space GL4R, modded out by SO13, provides the gauge space for symmetric teleparallelism. These are gauge symmetries in the same sense of Yang-Mills theory, which is mathematically more rich than the definition considered by Dirac, as Yang-Mills theory contains a gauge group G in addition to the global spacetime manifold. It is also well known that the local translations and the general linear group play an important role in approximating global diffeomorphisms. Additionally, we should assume that these quadratic Yang-Mills-like teleparallel theories have dynamics in the gauge fields, whose gauge symmetry is known to be a subset of the global nonlinear diffeomorphisms. Therefore, there is decent intuition suggesting that the Tominaga-Schwinger equation in the field strength formulation of the teleparallel equivalents may have valid quantum evolution. Now, to actually obtain rigorous quantum gravity, this is a tall feat, as we don't even understand any physical quantum field theory in a rigorous manner. However, we must, at least at the level of rigor that is on par with other works in quantum field theory, provide something to claim that one has successful quantum gravity, especially if one does not provide explicit solutions. We do not claim to have solved quantum gravity in this work. Instead, we propose a formulation that will allow for the study of quantum gravity to validate whether it has improved behavior in comparison to general relativity or not. This is not meant to directly resolve issues of UV completion of general relativity or the teleparallel equivalence. I envision that other modifications will be required to solve that issue, but for now, I am primarily focusing on the problem of time, and more specifically, the frozen formalism as a facet of the problem of time. But even if we could get dynamical evolution of quantum gravity, what is more important is that the infinities can be tamed. One strategy is that the hypersurface deformations do provide a natural suggestion of a point-splitting regularization scheme, which can introduce a mollifier, which is basically a prescription to assign a density to integrate over the hypersurfaces and apply an averaging procedure. Essentially, the goal is to work with a variable epsilon, such that when it is finite, we get infinity problems, but when we take the appropriate limit, we recover a finite solution, such that one may apply a renormalization procedure that can regularize the infinity issues associated with quantum field theory, and more specifically with quantum gravity. Once again, we are not claiming to have solved this problem, but we can present a sketch of a specific regularization procedure that can be used to study this problem further. By averaging over this hypersurface, we can take any physical quantity and apply this function that depends on epsilon, so that when we take the limit of it as it approaches zero, we recover some notion of regularization. There's a fascinating weird thing in quantum field theory where it is convenient to consider you to be in 4 minus 2 times epsilon dimensions, whereas as if epsilon is infinitesimally small or something like this. In a similar spirit, we use an epsilon parameter that allows for some kind of interpolation to recover tame dynamics within a limit, or even right on one side of a singularity, yet approaching that in a limit. So when we get a valid field operator like the metric in symmetric teleparallelism, we can average it over the hypersurfaces as we evolve it to obtain a regularization scheme for quantum gravity, at least in principle. This allows for the Hamiltonian and the deformation operator to be regularized such that a renormalized quantum gravitational wave functional can be found within the Tominaga-Schwinger equation. The deformations of the hypersurface evolution track the Noether currents associated with the energy and momentum transfer as the system evolves through Hamiltonian analyses that remain covariant, canonical, and presymplectic. To propose a regularization scheme for infinities that is natural for this hypersurface evolution, therefore, in order to obtain a regularized version of the Tominaga-Schwinger equation for the teleparallel equivalence to general relativity, consider the following Tominaga-Schwinger equation, which uses the renormalized quantum deformation operator as the proposed evolution operator. The Wheeler-DeWitt equation was found after a meeting between Wheeler and DeWitt when one of the scientists was waiting around at an airport due to a delayed flight. If that flight was on time, a spark, the thought of an idea, might have never came to humanity in the same way. Enamored with excitement, an equation was written down and called the Einstein-Schrödinger equation, as it was thought by DeWitt that his theory would describe how the quantum evolution of general relativity could be evolved. Rather than working with a typical wave function in a Hilbert space as in quantum mechanics, a quantum mechanical wave functional of fields is considered, which is associated with a Hilbert or Fock space that encodes the states of non-perturbative quantum gravity. If this equation works, it should unlock the holy grail of quantum gravity. This equation was referred to as the Wheeler-DeWitt equation, which turns out to not evolve the quantum states. This should have been clear from the get-go, as the canonical Hamiltonian of general relativity using Dirac's approach leads to a Hamiltonian that vanishes. However, people felt like if they brought this Hamiltonian to a quantum operator, it would somehow bypass these issues that are hinted at the classical level. A more sophisticated approach is to study quantization in light of de Donder-Weil mechanics, which has a rigorous treatment of classical field theory with fiber bundles used to describe quantum fields as sections of jet bundles and is related to multisymplectic geometries. However, the sole pioneer of researching the quantization of de Donder-Weil mechanics revolves around the work of Igor Konachikov, who has been elaborately writing on this topic for decades. However, his work has a few generalizations that are difficult for many to grasp. Even the prolific Thomas Thiemann, who writes textbooks for breakfast and even has work on unified loop quantum gravity with supergravity, giving what he calls loop quantum supergravity, even while he strolled the halls of Harvard, he cited Konachikov's work only briefly and referred to it as rather difficult. This is partially because Konachikov uses a Clifford algebra-valued wave function. By coordinatizing the fiber space and not the sections of the fiber bundle, Konachikov obtains a wave function, but not of abstract field coordinates, and not space-time coordinates either. This brilliant leap also is grounded in Clifford algebras in a manner that the classical multisymplectic geometry community does not prefer. So, most of the mathematicians that are capable of understanding what Konachikov is saying do not want to work with what he is doing, despite it being one of the most rigorous and worked out examples of covariant quantization of field theories to date. I digress. Needless to say, it would be worthwhile to investigate whether there is some generalization of the Wheeler-DeWitt equation that is structurally closer to the original intuition of the idea. The Schrödinger equation evolves states in quantum theory, while quantum field theory also admits the notion of a quantum wave function. By introducing a Hamiltonian density that does not identically vanish due to Legendre degeneracy, those primary Hamiltonian constraints initially found in the Dirac analysis, it is hoped that the quantum operator may provide improved quantum evolution, at least in relation to the frozen formalism as a facet of the problem of time. So, there became this thought, what if the problem of time is actually a feature, not a bug? What I mean by this is the notion that the derivative of a wave functional equaling zero can be mathematically true, just like that which is found within the Wheeler-DeWitt equation. However, the difference here is that this differential operator is constructed with the hypersurface deformation operator acting as a gauge field in the Hilbert bundle. This allows for one to expand further and subtract the gauge field to the other side such that the Tominaga-Schwinger equation is derived from a principle of timelessness in the sense of a covariant Hilbert bundle. Remarkably, what we found is that in order to obtain anomaly freedom, we could frame it as a notion of teleparallelism on the Hilbert bundle itself, not teleparallelism in space-time. This is a really super abstract idea. So if the hypersurface deformation generator is treated as a classical field, and then we map that to an operator for quantum observables that generate non-perturbative quantum gravity evolution, then it seems the evolution is only consistent if the Hilbert bundle curvature vanishes. Even more curious, it turns out that the unitary evolution is found precisely when the Hilbert bundle non-metricity vanishes. Intuitively, this is because the notion of unitarity is connected to conservation of probability flow, which states that the total probability must sum to 1. The length of the vector can never change lengths when transported around the entire universe. This implies that the Weil non-metricity vanishes, as we want to preserve the length associated with the total probability of a normalized wave functional, which should sum to 1. Not infinity or any other number. Once again, we don't have proof that the Hilbert bundle is geometrically flat, but the statement can be made in this way. If one can prove that the Hilbert bundle is flat and metric compatible, then anomaly freedom and unitary evolution emerges. Otherwise, quantum path evolution would not be path independent. Since there are many various paths that are infinitesimally close to each other, one might think that this path independence should be found, but it also could be pulling too much from intuition of classical field theory and Minkowski spacetime. However, the consensus within the community is that consistent quantum gravity must be free of anomalies, which is associated with this notion of path independence. If the flat and metric compatible Hilbert bundle is found, then if one studies a Tominaga-Schwinger equation for one of the teleparallel equivalents to general relativity, where the velocity field is assumed to be the field strength, such as torsion or non-metricity, then the local gauge formulation is quite a natural approach. And one can define a covariant Hilbert bundle derivative that acts on wave functionals to provide diffeomorphism or other gauge symmetry deformation to non-perturbative quantum field theory. And simply stating that this covariant derivative vanishes on the wave functional, it is possible to obtain the Tominaga-Schwinger equation. Since the teleparallel equivalents do emit gauge-theoretic structure, it is suggestive that they might allow for dynamical evolution, although one must rigorously prove that first, the deformation operator does not merely generate gauge-redundant information, and second, that the evolution is anomaly-free, such that path-independent quantum evolution can be obtained. The bold conjecture that I should take some caution with proclaiming is the notion that teleparallel quantum evolution might actually transcend spacetime into the Hilbert bundle that contains the structure for the quantum evolution of the quantum fields themselves. At the end of the day, this work is more inspired by the Tominaga-Schwinger equation than the Wheeler-DeWitt equation. But we can also see how the notion of timelessness compares in general relativity versus teleparallel theories. One thing we can say for sure is that there is a trivial way in which the Hamiltonian vanishes in canonical general relativity, which does not occur in the field strength formulations of local teleparallel theories. In summary, we have introduced a new framework for analyzing a wide variety of theories. We took multisymplectic or polysymplectic geometry found in Dodonder-Weil mechanics, which provides mathematically rigorous classical field theory, and generalized that further to consider field strengths themselves as velocity fields. We refer to this as the field strength Hamiltonian formulation. This finds so-called superpotentials, generalized momenta, excitations, or generalized polymomenta as natural variables of a generalized multisymplectic phase space. By taking these methods and combining them with covariant phase space methods, presymplectic geometry on hypersurfaces can be found, while symplectic geometry is found by removing the gauge redundancy in fields. This obtains a result that is covariant, canonical, and symplectic, which is exactly what Witten was going for with his study of covariant phase space methods. And even though Wald independently studied the same structures for quantum field theory and curved spacetime, neither groups ever explicitly wrote down a Hamiltonian formulation. This work connects the dots by showing how the Hamiltonian from DDW mechanics or the field strength Hamiltonian can be brought into the presymplectic geometry while retaining manifest Lorentz covariance. The covariant phase space methods bring in the notion of hypersurfaces, which naturally suggests a connection to the Tominaga-Schwinger equation. Here, the hypersurface deformation operator can be found in terms of the Lagrangian or the Hamiltonian. However, it is natural in quantum theory to quantize phase space, not position and velocity. For this reason, framing everything in the Hamiltonian rather than the Lagrangian is the natural framework, as it depends on the position and momentum. And this is why we can use the Hamiltonian and more easily obtain a Tominaga-Schwinger equation in terms of these quantum operators. And finally, all of this machinery was introduced to prepare to study the quantization of the teleparallel equivalents to general relativity. We found that the field strength Hamiltonian formulation successfully captures the classical equations of motion. We also provided a prescription on how to carry through with quantization. While we did not solve quantum gravity by any means, it is curious to note how the proposed dynamical evolution compares to general relativity. GR leads to a problem of time, largely because the Hamiltonian is constrained to vanish, but also because any attempt to evolve the system ends up leading to gauge refoliations of spacetime that do not actually evolve the system, but rather provide unphysical transformations. Specifically, with the teleparallel equivalents, we find that there are no Hamiltonian constraints due to Legendre transformation degeneracy, specifically when using the field strength Hamiltonian formulation. Furthermore, the analysis of the bulk versus boundary hypersurface evolution suggests that we could be getting quantum evolution due to the notion of how these theories are now gauge theories. However, I must add as a final disclaimer that once again, more work is needed to demonstrate whether teleparallel equivalents have improved quantum behavior, but I believe this work suggests that there is hope that the frozen formalism can be avoided or at least bypassed in some way. Skeptics may claim that the equation may only lead to gauge refoliations, but there's two things that are different than GR. First, we obtain this non-trivial Hamiltonian and quantum hypersurface deformation operator, and then second, the teleparallel equivalents are local gauge theories in the Yang-Mills sense, unlike general relativity. So it seems plausible that the teleparallel equivalents might lead to evolution. Also, in my opinion, The biggest problem with quantum gravity is the UV divergences, not the problem of time. I doubt that this formulation applied to the teleparallel equivalence will solve this problem. However, it is plausible that the teleparallel equivalence could be modified with high-energy terms, which could change the UV behavior. To rigorously take the next step, it would be nice to analyze whether anomaly freedom can be found. Curiously, we showed that in order to obtain anomaly freedom, a certain Hilbert bundle must exhibit a teleparallel space with vanishing curvature. This is not the curvature of spacetime, so there is no reason why teleparallel spacetime should lead to teleparallel Hilbert bundles. However, I can't help but point out that teleparallelism considerations in general might turn out to be a guiding principle for quantum gravity. So, to conclude, there is a lot more work needed to demonstrate that we have a sensible notion of quantum gravity, but I hope this video was at least educational for aspects of quantum field theory, metric affine gravity, and quantum field theory. However, I hope this video was at least educational for aspects of classical field theory, metric affine gravity, and quantum field theory in general that are seldomly taught in graduate school. If you've reached this far, then I'd really appreciate if you leave some comments below or ask any questions. Also, if you haven't yet, like and subscribe for future updates. And finally, a big thanks to you, the listener, as I really appreciate you taking the time out of your day to listen to me talk about my research in theoretical physics. All right, signing off for now and have a wonderful day.